In this video, we're going to finish our discussion of sets, and we're also going to look at, so this is sets part 2, and we're also going to look at just the very beginning of chapter 3, which is logic. So sets part 2 and intro to logic. We are going to start with more discussion on cardinal numbers. We're also going to talk about surveys, which is part of your discussion board assignment for the week. And then we're going to finish off with talking about logic, symbolically representing statements. You'll figure out what that means, and how to work with those symbols. So let's go ahead and start with more on cardinal numbers. So first of all, we want to look at cardinal numbers. So cardinal numbers, which is the size of a set, so the cardinal number for a union of sets. So let's give ourselves two sets. How about A is 3, 4, 5, and 6. And then set B, let's say that set B is 3, 5, and 7. We're going to look at our cardinalities. So the cardinal number, or the size of set A, n of A, is equal to, it has 1, 2, 3, 4 elements. We also want to know what the size of B is. So the cardinal number for set B, it has 3 elements, so that's 3. And then finally that union. So if I want to know what the number of that union is, the number of elements in union A union B, I can do a couple things. I can start by actually looking at the union. So I'll put it here, A union B is the set of all elements. So the set of all elements, let's go ahead and start with what's in A. So they need to be included, 3, 4, 5, and 6. And then I need to include whatever I left out of B. So 3 is already there, 5 is already there, so I really need to include the number 7. So 7. And from here I can figure out what that cardinal number is. 1, 2, 3, 4, 5. So my cardinal number is 5. If my sets were bigger, though, I wouldn't want to have to look at the union, actually compute what's in the union, because I don't care what's in it. For this question, I just care about how many there are. And we're going to see this applied to the surveys when we do those in just a minute. So if I put everything together here, I find that the number in that union, so the number in A union B, is, remember how I started by writing out the elements in A, is the number in A, plus we added any elements from B that weren't already in there. Another way of saying that is we're going to add elements from B that aren't already in there. So really what I excluded were these values that are in the intersection. So I added elements from B, but not in the intersection. What I'm really doing is I'm adding these together, and then I'm taking away any that I've double counted. If I just add the number in A, which is 4, plus the number in B, which is 3, I'm double counting the 3 and the 5. So what I need to do is to take away who is in that intersection, and that intersection, A intersect B, is the common 3 and 5. So the number in that intersection is 2. So I started with a simple one, 4 plus 3 minus 2 is equal to 5, so that we can move on to one that has a different set of information. It's easy when you've got small sets to work with and you're given the entire set. Let's take a look at this example. So in a second example here, let's say that's my first one. So in a second example, we're not given the elements of the set, but we're given information about them. So in the first set, capital X, we have 7 elements. In the second set, capital Y, we have 10 elements. And in their intersection, so X intersect Y, we have 5 elements. If I want to find the number in the union, X union Y, I need to add the number in X plus the number in Y, but I need to subtract anything that was double counted, which means I'm subtracting the number in their intersection. X intersect Y. So now I just plug stuff in. So I've got 7 elements in X. I have 10 elements in Y. that I have 5 elements in common, and I double counted those, so I've got to subtract my 5 out. Okay, so that would be 17. 17 minus 5 is 12. Oops. Okay, one more. So in this one, we have yet another slightly different set of information. So in our last example here, let me move everything up. So in our last example, we are going to start with this information. Okay, so we've got the number in the union, so C union D, is 15. So we're given the number in the union. We're given the number in the intersection, so C intersect D is 3. So there are 15 different elements altogether between C and D, 3 elements in common, so the union and the intersection. And we're also given that the number in C is 10. The question is, find the number in, well, you guessed it, that would be D. So if I'm looking for the number in D, I'm going to use my formula. I know that the number in the union, C union D, is equal to the number in C plus the number in D minus anything I double counted, which would be the number in C intersect D. I've got some of this information, but not all, so let's plug in what we've got. The number in C union D is 15, so that goes there. The number in C I have. The number in C is 10, so that goes here. I don't have the number in D, but I do have the number of elements in their intersection, and that is 3 minus 3. Okay, so now I do the math. Just a little teeny tiny bit of algebra. So I have 15 equals 10 minus 3 is 12. 12 plus the number in D. So that means that I needed 3. 12 plus 3 is 15. So the number in D must be 3. 12 plus 3 is 15, and that makes that equation true. So we can look at these in several different ways, but I'm using that same formula, which I've got right up there. I'll put an orange box around it. So for these first kinds of questions dealing with cardinality of a union, I'm going to use that same formula. So the number in the union, number of elements in the union, is the number in the first set plus the number in the second set, and then I subtract any that might be in their intersection. So I subtract any that were double counted. We're going to apply this not in a formula sort of way like we've got here, but we're going to apply this more in a conceptual way as we're working through some surveys. So let's take a look at some surveys. This is related to your discussion board assignment for this week. I'm just going to do an example. As we're doing a survey, what we're really doing is we're taking a look at relationships between different sets or different results, and I think the best way is just to give you an example. This one's actually similar to one in your textbook. Okay, so Joe writes and produces music projects. He worked 10 projects. Of the 10 projects, he wrote and produced. So he wrote and produced 2. He wrote a total of 5 projects, and he produced a total of 7 projects. And then we've got some questions. I'm going to actually pose the questions here so you can see how we want to proceed. So the first one is, how many projects did he write but not produce? We are going to solve this with a Venn diagram. It's the easiest way. So as I'm solving this with a Venn diagram, I notice that we've got 2 different sets or 2 different scenarios here. So we've got writing as a set, producing as a set. And what we're given here are the number of projects, not the names of the projects, but the number of projects. So if I let W be the set, so this is the set of projects that he wrote, and P is the set of projects he produced. I can use cardinal numbers and a Venn diagram, that's really the key here, to solve this. Okay, let's actually start down here. He produced a total of 7. So that means that the number in set P is equal to 7. He wrote 5, so the number in set W is 5. He wrote and produced 2. So wrote and produced, that means we're looking at the number of sets that, or the number of projects, I should say. So this is the number of projects where he did both. So these are the projects that are in the intersection of those two sets. So the number and is intersection. So wrote and produced. So they share these in common is equal to 2. Okay, so I'm going to quit with my symbols and move on to a Venn diagram. So we're going to take this information and put it into a Venn diagram. Okay, so here comes our Venn diagram. So I've got 2 different sets that I'm working with. As I put my 2 sets together, so I've got a set here. They overlap because there's something in their intersection. So there are my 2 sets. It's a Venn diagram, so I can even draw a box around this. So I can think of my universal set as the set of all of his projects. So the universal set is the set of all those projects. And I know that the number in the universal set, he worked on 10 projects total. So there it is, 10 is equal to 10. Okay, so this is going to be the set of projects he wrote and the set of projects he produced. And I can start filling these values in. I'm going to start with the one where the intersection is. So I'm going to start with wrote and produced. Well, that's this football shape right here. That's their intersection. That's going to be 2. So I've got that one done. He wrote a total of 5. So the entire set here, W, has 5. I've got 2 so far, which means that the rest of the set has size 3. So that takes care of this one. The number of produced is 7. Well, here's my produced set, which includes that 2. So if I cover this up, I've got 2 so far. I need 7 total, which means that in there, I'm going to end up with 5. So I've got 2 total, or 2 plus 5 total in produced. So number in the produced is 7. And then I have 3 plus 2 in the set that he wrote, and that is 5 total. And I have 2 that he both wrote and produced, so 2 in the middle. So now let's take a look at that question. How many projects did he write but not produce? So I want to be in the right only. So this one he produced. This is the right only. So now I can answer that question. That was 3 of them. Here comes another follow-up question. Number 2. How many projects did he produce but not write? So if I want the projects that he produced but didn't write, here's my produced set, but those 2 are ones that he produced and wrote. Here are the 5 that he produced only. So that's going to be 5, and my answer there is 5. Okay, so that's an example of a survey with 2 different sets. The next survey has 3 different sets. So here comes the next one. So next example, we'll do 2 of these. So here's the next example. In a class of 20 students. So now you should be thinking ahead. So I'm talking about this class of 20 students as everybody. I'm going to break things down from here, which means that my universe is the set of students, and the number in my universal set is 20. Okay, so here comes how I'm going to break it down. 5. We have 5 total business majors in this class. 11 total math majors, because math is such an awesome major. So 11 total math majors. 4 are majoring in business and math. I left one off. 8 total engineering majors. Okay, we already got the 4 in business and math, so let's move down to 5. 5 are majoring in engineering and math. So 5, engineering and math. Nobody is business and engineering. And then finally 2 are all 3 of these majors. So that's a lot of information. Let me start off with the questions. So question number 1. We want to be able to answer this. How many are majoring in math only? We also want to know how many are majoring in business and math, but not engineering. So number 2. So business and math, but not engineering. And then finally, question 3, how many of the 20 students are majoring in none of these majors? So how many are majoring in none of the 3 majors? And we could have an English major, right? Or a music major or something. So none of the 3 majors. Well, what we need is a Venn diagram. This time we have business, math, and engineering. So as I set up my Venn diagram, I want 3 interlocking circles, and I'm going to draw those so that they connect in the middle also. So you're not going to be able to see all of that because I need to get my Venn diagram up here also. Okay, so I want 3 of them. So 1, 2, and then I'll put the third one down here. So these live in the universal set, which is my class of 20 students. Okay, so U is equal to my class. The number in U is equal to 20, which we may or may not need. As I put my information in here, I need to first label my circles. I need 1 for business, so there's the set of business students, 1 for math, and 1 for engineering students. And the order doesn't matter, you can label them anyway. When I start these, I look for the information where I have the most circles overlapping. So I'm going to start with this information right here. 2 are all 3 majors. So I'm going to go ahead and put a 2 right here. 2, all 3 majors. And then I work up, and I'm now going to look for the ones where 2 sets intersect. So now I'm looking for math and engineering, business and math, or business and engineering. So I'm really working my information up backwards. So next I need, so the second piece of information, I'm just going to work my way up, is 0 in business and engineering. And you know what? That really should say 2, shouldn't it? I'm going to change that to 2 because I already have 2 that are business and engineering. I just miscopied that, so we'll put 2 there. Okay, so 2 are in business and engineering. So you cannot change your own problems. If you're working your own problems at home, they should already be worked out. But I just miswrote that. Okay, so 2 in business and engineering. I already have 2. This is what should have been 0. So there are 0 right there. So make sure you make that change. So 2 in business and engineering. Let's look for another intersection of 2 sets. Engineering and math, there's another one. So number 3. So engineering and math. Engineering and math is this football shape right here. I've got 2 so far. I need 5 total, so I need 3 more. So I've got that one. And then I'm looking for the last one that are 2 sets together. And the last one that's 2 sets together is business and math. So this one comes next. 4 major in business and in math. So business and math is this football shape here. I've got 2 so far. I need 2 more. So that gives me my 4 total. Now I work my way back to the single sets. So now I want the total business, total math, total engineering. Let's go ahead and start with the total engineering. So the total engineering, I'm going to call that number 5. The order now doesn't matter because I'm just working with the entire sets by themselves. 8 total engineering. I've got, so far in my engineering circle, so you can cover the rest of this up, my engineering circle, I've got 5 so far. I need 8, which means that I need 3 more in engineering only. See how that works? So total engineering is 8. I already have a 2 and a 3 for 5. To get myself up to 8, I need 3 more. Okay, let's move to the next one. So now let's do math majors only. 5. Okay, so of our awesome math majors, we need 11 total. In the math circle, I've got so far 2 plus 2 plus 3. So far I've got 4 plus 3 or 7. So I've got 7 so far. I need 11 total, so I need 4 more. So if I add up these numbers in the math set, 4 plus 2 is 6, 6 plus 2 is 8, plus 3 is 11. So I have 11 total math majors. Last but not least are the business majors, information number 6. So for that one, I've got 5 total business majors. So far in this business set, I've got 2 plus 2, which is 4, and I need 1 more. Okay, so I've got my Venn diagram filled out. Actually, I have everything filled out except what's on the outside, but I'm going to see if I need that when I'm answering the questions. So let's move up to the questions. Now it says, how many are majoring in math only? Math only are these 4. Okay, we don't want them to intersect with any of the other majors. So math only, there are 4 of them. How many are in business and math? So let's see, business and math. So I'm here. So business and math, but not engineering. So I'm really just here in this group. So business and math, but not engineering. It looks like that little Star Trek emblem. That's going to be 2. So there are 2 in the business and math, but not engineering. So there's 2. I do need the number on the outside. How many are in none of these 3 majors? Remember I said there could be an English major or an art major. To figure that out, I need to add up all of the cardinalities that I see and decide how many I've accounted for out of my 20. So in those Venn diagrams, I've got, let's go inner and then work our way out. So I have 2 on the inside. In my intersections, I've got 2 plus 3 plus 0, so 2 plus 3. And then along the outside, I have 4 plus 3 plus 1, plus 4 plus 3 plus 1. So if I add these up, let's see, there's a 10. So I've got 10 and 5, so I have 15 in the 3 majors, so 1 of the majors. But I had 20 total. So that means that 20 minus 15, which is 5, are none of those majors. So I can actually put a 5 out here. Now I can double check myself by adding up all of these numbers, including the 5, and I should account for the cardinality of my universal set, which is 20. So in other words, I should be able to add up all the numbers and get to 20. Okay, so how many are none of those majors? Well, I had 15 that were 1 or more of the majors. So to be none of the majors, that leaves me with 5. So how many are none of those majors? That is 5. When I built this problem, I didn't start with the given information. So thinking about your discussion board assignment, I did not start here with the given information. What I did to build this problem, and I'll just kind of give you a little hint, I actually started with my 3 sets, and that's also how I caught my error there. I started with my 3 sets. I decided what I wanted my 3 sets to represent. You know, maybe these are people that have a dog as a pet, a cat as a pet, and a bird as a pet. And then I just started to fill in my numbers, and then I can put my information together. So maybe one person has all 3, and then I've got 2 here, and 3 here, and 5 here. And then I just keep going, and I've got 4, and then 6, and then 8. So I figure that out, and now I can give information. So the total bird owners. So see how I can start building my information? I've got, let's see, so what is this? 4 and 5 is 9. 9 and 8 is 17. So total bird owners is 17. And then I can do total cat owners. Is going to be, let's see, 3, 8, and 4 is 12. And then the total dog owners, is going to be, let's see, that's 12. It's going to be 12. And then I keep going. So then I can say bird and cat is 6. and then, so that's this guy, bird and cat is that football-shaped intersection. And then I can say cat and dog owners. Cat and dog owners is 3. See how quick these are to put together? They're really complicated if you're trying to start with the given information. But if you start with a Venn diagram and fill in your numbers, then you can come up with your answer. You can even finish this off and you can say, of 30 people that we surveyed, make sure that these all add up to less than 30. I'm not guaranteeing that they do because I just grabbed that out of the hat. Of the 30 people we surveyed, here's what we came up with for people that owned a pet. So anyway, that's how you can come up with your discussion board survey. So take a look. I've got a sample online. These 2 examples should help. But I really recommend that you start with your Venn diagram first. Watch for typos, like I had. Watch for typos, and then work from there. Okay, so those are our surveys, which was, I think that was section 2.4. And the last section in the sets is section 2.5, which is more on cardinality. So we're looking really at cardinal numbers for infinite sets. So sets that have infinitely many numbers. I want to start off with our choices. So our choices, we could either have aleph not, which I believe is a Hebrew letter. So aleph not. To create the aleph symbol and to keep things simple for me, I do a straight line. It's like an X, but I do a straight line for that side of the X, and then a curved line for this side of the X. The not is a subscript 0. So that's aleph not. The other one is, or a lowercase c, and the c represents a continuum. And that can help you remember when we go through the example. So I wanted to start there. We're going to start with aleph not, though. So the number in a set is equal to aleph not if the set is countable. Okay, so what does that mean? Countable, it can mean a couple different things. It means that you can list the values in the set in some kind of an order. If you can list them, that means that you have a 1-to-1 correspondence with the counting numbers. Counting or natural numbers, same thing. I'm running out of room. Counting numbers. We need an example. Let me get another piece of paper here. Okay, so for example, let's look at this first one. The set of all x's such that x is a multiple of 100. Multiple of 100. If I want to list the set out, I can. So I've got 100, 200, 300, 400, and so on. Which really means that I have a first element. Here comes my 1-to-1 correspondence. I have a first element. I have a second element. I have a third, a fourth, and so on. So see how I can say this is countable? Because I can assign each of these values to a counting number. So this is the set of natural numbers or counting numbers, and I've created a correspondence between that set and my set, which means that the number in the set, so the number in this set here, number in that set, is aleph not. Okay, second example. Let's look at the integers. Okay, so the integers, dot, dot, dot. -2, -1, 0, 1, 2, dot, dot, dot. And we use a capital Z with a double bar to represent the integers. Well, in this form, I really can't do a 1-to-1 correspondence with the counting numbers because the counting numbers have a starting place. The way that I have it listed here, I don't have a starting place or an ending place because I go forever in the negative direction and forever in the positive direction. But if I reorder this, starting with a 0, and then my ones, 1, -1, 2, -2, 3, negative 3. See how I can establish a starting place? This is part of being countable. And then I have a pattern that tells my reader how to count or list the numbers in my set, dot, dot, dot. Okay, so here comes that one-to-one correspondence. I have a first element now, a second element, a third, a fourth, I get tired of drawing all these arrows, a fifth, a sixth, I've got one more, a seventh, and so on. So here are my counting numbers, dot, 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 and I've established a one-to-one correspondence. Okay, so how about this one? So for the next one, let's do, oops, so many set brackets. Okay, so for the next one, let's do the set of odds. So x is an odd counting number. Okay, well what I need to do first is to figure out what's in there and then decide, to be countable, remember it has to have a designated first element, and then I have to have a specific pattern to get through all of my elements in a list. Okay, so odd numbers. That would start with 1, 3, 5, 7, 9, 11. And this is an odd, and I said it but didn't write it, counting number. So I'm not doing any negatives. Counting number. Dot, dot, dot. Okay, I definitely have a first element, and I have a definite list. So I can just say that this is a one-to-one, and I'm going to write it this way to shorthand. I have a one-to-one correspondence with the counting numbers, which means that my set is countable. So just giving you some more vocab. So my set is countable. And finally, the number in my set, let's call my set A. So the number in my set, it's infinite for sure, it keeps on going, but I can say that it's infinite with this order, this one-to-one correspondence. So it's infinite, and I can give it a cardinal number of aleph naught. Can you think of a set that's infinite that is not countable? If it's not countable, we're going to use that value C. So there are a couple common ones that we're going to look at. We're not going to look at a lot here. So the set of real numbers. The set of real numbers, we don't even really define the set of real numbers, right? Those are all my irrational numbers and rational numbers, and it's everything. Here's how I can define it. Everything that you can find on this number line here. Oh, remember how I said C was a continuum? So my real numbers, I could give you examples of real numbers. That would be like a 5 or a negative 17 or a pi squared or a square root of 27 or negative 5/8. I mean, there's so many, but there's no definite order, and there's no definite, I just grabbed 5 out of a hat. This is not the first real number. It's a continuum. And because it's a continuum, we say that the cardinal number for the set of real numbers is C. The set is not countable. I can't establish a first one. I can pick anything to be the first one, but then I don't end up with a definite order after that. You could try, but it's not possible. Another set that's like this is the set of irrational numbers. Irrational numbers have no end to their decimal and no pattern to their decimal places. So the set of irrational numbers contains things like radical 3 or pi squared, like I've got up there, pi squared, or the value e, which is 2.71828, dot, 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 on and on forever. Also not something that you can order, which means it's not countable. And the number that we assign to the irrational set, also infinite like the others, but this is C. We think of these as being bigger. So we think of C as being bigger than aleph naught. And it's because the set of natural numbers, okay, see if you can follow this. Remember, if you were aleph naught, you had a one-to-one correspondence with the natural numbers. But the natural numbers, 1, 2, 3, 4, 5, 6, 7, are all real numbers. The set of natural numbers is a proper subset of the real numbers. To be a proper subset, you have to be smaller. So C is bigger in scale, even though they're both infinite. C is bigger than Aleph naught. So you can just kind of think about that one. One last topic in this section, and that's equivalence. Equivalence of sets. Set A is equivalent to set B if the number in A is equal to the number in B. So that's equivalent. So, for example, we had A, which is the set of all odds, the odd counting numbers. And then we had the counting numbers. Oh, counting numbers, natural numbers. 1, 2, 3, ... Both of these cardinalities, so the number in A was equal to the number in the natural numbers, and both of those were Aleph naught, which means that these two sets are equivalent. So set A is equivalent to size only, equivalent to set N, but note that A is not equal to set N, the set of natural numbers. To be equal, remember, they had to have all the same elements. Equivalence just means that they have the same size. Okay, so for example, let's do set B and say that B is all the x's such that x is, we'll do an even number, and the reals. So the question is equal, equivalent, or both or neither, I guess. So for this one, if B is the set of even numbers, I can list those with a definite starting place. 2, 4, 6, 8. It's countable. So the number in B, the cardinal number, is Aleph naught. And we know that the cardinal number for the reals, because it's not countable, is C. They don't have the same size. This is a larger infinite cardinality than this one, which means that they are not, that's supposed to be a B, they are not equivalent and not equal, obviously, not equal. Okay, so equivalence has 3 lines, and then equals has the 2 lines. Okay, so that finishes up the discussion on sets. We do want to do some more with the, start, I should say, with some introduction to logic. This really follows what we've done in the sets a little bit, so it's a nice place to have it. So introduction to logic. This will be on your exam. This is 3.1 in your textbook. When we're using logic, what we're really doing is we're taking English statements, words, and we're analyzing them symbolically. Analyzing them symbolically. I think this is pretty fun, and I've got some great articles to read and some things that you can do with this, but you've got to get used to the notation first. So we're talking about these English statements. So first we need to define, or at least by example, what a statement is. So first of all, a statement. I'm just going to say it this way, and you'll see with some examples, it's not a question or an opinion. Opinion. Okay, so for example, and we assign these two letters. So I'll say that statement P is this. Today is Tuesday. It might be when you record this, but as I'm recording this, it's actually Friday. To be a statement, it doesn't have to be right or wrong. That doesn't matter. This happens to have a false truth value. But just the fact that I can determine if it's true or false tells me it's a statement. So this one is a statement. So I'm just going to say yes. Okay, so it could be false, it could be true, but it has to be not an opinion and not a question. Okay, so here's another one. So Q. I think Proposition 1 will pass. This one is actually an opinion because it's about what I think, it might pass and it might not pass, but I'm making an opinion about what I think will happen in the future. Some of these are kind of hard to determine, but this one is not a truth statement. If I changed this and I instead said that Proposition 1 passed. Okay, now I can look, after the election is done, I can look at the results and determine its truth value, if that's either true or not. So in this form, if I change it just a little bit, the answer is yes. Okay, here's the next example. Where are you? This doesn't have a truth value of true or false. Where are you has an answer. So I can say that I'm at Wenatchee Valley College right now. You might say that you are in your home in OMAC. So where are you is not a statement, it's a question. So it does have some kind of a value, but not a truth value. I can't answer this one true or false. So you have to be able to answer or respond to these as true or false. So this one is no. Okay, so those are some statements. Let's take a look at some more examples of statements, and we're going to look at negating statements. Okay, so B, negating statements. Okay, so that first example that I had, P, today is Tuesday. Today is Tuesday. And remember I said when I'm recording this, it's actually Friday, so I can assign a truth value to this. For me right now, this is false. If I do the negation, which means I want to change this from a false statement to a true statement, I'm going to write this little tilde in front of my P. So the negation of P is just today is not Tuesday. Don't worry, they get harder. Okay, so I said today was Friday. So that's true. Today is not Tuesday for me. True. Okay, here's another example. Everybody, so I'll call this Q, everybody will get an A. Okay, now that is either true or false. I'm not stating my opinion. You're at the end going to be able to figure out if you get an A or not an A. So everybody will get an A. This isn't probably true, although if you all do, awesome. I am not opposed to giving everybody an A. If I want to figure out what the negation is, I write the tilde in front of Q. I want you to be really careful. The negation of this, so remember I said that this is actually false. Not everyone's going to get an A. Probably. So I'll just say, for the sake of our argument, that that one is false. If I want to give it the opposite truth value, that's what a negation is. I'm not going to change everybody to nobody. What I want to do is I want to make this false. And to make this false, which is more realistic for this one, I just need to have somebody who doesn't get an A. So I'm going to change everybody to at least, oops, I didn't spell that right, at least, that says least, one person will not get an A. Okay, so if this is false, at least one person will not get an A. That does make it true. What I've done, and here's the trick, is to change my quantifier. Everybody makes that a blanket statement, and it's really hard to have a true blanket statement. Everybody is a universal quantifier. At least, because I'm talking about one or more, so at least one or more is existential. So we start with exist. So existential. Oh, is it T-I-A-L? I always forget. Yes, okay, existential. So this really is at least one person. So if I'm negating something that has, these are quantifiers, I've got my room down here. If I'm negating something with a quantifier, I'm going to change between universal, which makes it a blanket statement, to existential, which exists. There's at least one. Okay, we need another one. So here's another example. R. So for R, somebody will win, like the lottery. Somebody will win the lottery. Okay, so now you know how to work this. So that somebody says at least one person. This is existential, which is a lot to write. This is at least one person. The opposite of somebody winning is not everybody winning. So the opposite of somebody winning, at least one person, which would be one person or more. So I'm going to have the number of people that win is greater than or equal to one person. The opposite of greater than or equal to one person would be nobody. So I'm going to go to the opposite universal quantifier. So this is nobody will win. So it went from at least one to, in this case, nobody. You could also say everybody will lose. That would also work. So there's a couple different ways to attack these. Let's do one more with these. Okay, so for example, I'll use P again. Let's say that every day is sunny, which we know isn't true, although it's pretty close to being true where most of us live. Every day is sunny. Every is universal. So this is a universal quantifier. To negate this, I need an existential quantifier. So I change every day is sunny to, out of all these sunny days, to change the truth statement, I need to find at least one that isn't sunny. So I'll say at least one day is not sunny. Okay, and I'll do my last example with my how I got out of jury duty story. So I got out of jury duty as I'm sitting there in the jury box as probably, as they're interviewing the jurors, juror number 6. So I figured I was pretty much in for being on jury duty. We got to the point where the lawyers stood up and were asking the people in the box questions to decide if they wanted to keep them or not. And these questions kept coming up from one of the lawyers. He would ask us, do you think that every police officer is honest? And then he had other questions for us. Is every police officer honest? Do you think that every low-income person is a criminal? I mean, all of these questions all of his questions had universal quantifiers. And I must have given a big, huge eye roll because, of course, I'm thinking, well, what does he think we're going to answer? Of course, we're going to say, no, not every police officer is honest. No, not every person is a criminal, and on and on. So he said, well, it looks like you've got something to say. And I said, well, yeah, when you ask us questions with universal quantifiers, what do you expect us to answer? Remember I said these blanket statements are really hard to make true because there's always one person who isn't, at least one person who isn't. And after that, I was off jury duty. Yay, not that I haven't been called back. But anyway. Okay, so how do we negate that? Every police officer is honest. I just need to find at least one police officer who isn't. So I can say at least one police officer is not honest. Okay, so there's statements. That's negating. Kind of tough to do with the quantifiers, but really when you're negating, make sure that you're also switching not just the statement to honest to not honest, but also you're changing the quantifier, universal and existential. We're also going to combine statements, and this last topic is going to seem really, really familiar because we're going to do compound statements using an AND symbol. The AND symbol is an upside down V, which looks a lot like our intersection symbol. The OR is a right side up V, which is a lot like our union symbol. So as we're doing these compound statements, we can start combining them. Okay, so for example, Let's say that P is, I'll do today is Tuesday again. And for Q, I'm going to use it is sunny. And it actually is. There's a few clouds in the sky, but it actually is sunny right now. It is sunny. And I'm going to just start combining them. So number one, I want P and Q. So see how we're getting away from all that language and into symbols? It looks a lot more like algebra and like math. But really what this represents is today is Tuesday. And it is sunny. Number two, P or Q. And I always remember this because if it's upside down, it's almost an A, right? If I just do that, it's an A. So I always remember that that one is the and. Okay, P or Q. So then I just write today is Tuesday. Or it is sunny, which is a funny statement, but we'll go with it as we're just getting used to our symbols. Okay, number three, let's do a negation. Not P and Q. So not P, P is today is Tuesday, so that means I need today is not Tuesday, because that covers all the other possibilities. Today is not Tuesday. I gave you an and, so and it is sunny. I guess I need commas there, right? Comma, comma. Okay. Let's put a negation on the outside of the compound statement, number 4. So let's do the negation of P or Q. We're going to use De Morgan's laws. We saw these 2 weeks ago. With De Morgan's laws, I can bring that negation through, and this becomes equal to the statement not P. I negate the connector also, and the or turns into an and, not Q, exactly like the De Morgan's laws that we used for sets. So this becomes, okay, not P. P was today is Tuesday, so today is not Tuesday. Tuesday, I changed that into an and it is not sunny. So there's a lot more examples there. Let's, you know what, let's do one more, number 5. And I'm just going to do a negation here because I know they show up in your homework. Let's say that P is actually a mathematical statement. X is less than or equal to 2. If I look at my number line here, here's the number 2. Less than or equal to 2 are all of these, or 2. So if I want to negate that, I don't want these guys. Instead, I want anything that's not less than or equal to 2. So to negate that, I want everything not including 2, but greater than 2. So to negate this, I switch the symbol and I drop the equals case because I don't want the equals case. So the negation of P is X is greater than 2. I don't want less than, so I want greater than. I don't want equal, so I drop the equals case. Let's do one more like that with that negation. So Q, and then we'll be done. So Q, let's say that Y is less than -5. To negate that, I don't want less than, I want greater than. I don't have the equals case, so I throw the equals case in. So Q, Y is greater than or equal to -5. And that finishes our topics for the week.